Thank you, Purvi, and thank you to the organizers for inviting me to Vienna. Vienna is the town I've lived the longest in as an adult. Doesn't quite feel like home anymore, but it's wonderful being back. So I will talk about the Poincaré inequality for open sets in Rn. And so let's first decide which inequality I mean by that. So we say the Poincaré inequality is said to hold on D in Rn open if there exists a constant, positive constant, such that the L2 norm of F is dominated up to a multiplicative constant by L2 norm of the gradient of F. For all functions which are smooth and have compact support in D. And here we really just mean the L2 norm of the components of the gradient. So we write this out once. Partial derivatives of F dv 1/2. So the first thing you can say is that you actually can take the closure of this space with respect to the Sobolev 1 norm. So you could as well write this space over here. And the next thing you might notice is that if you have the Poincaré inequality, then this Sobolev 1,0 space is not just a Hilbert space with respect to the Sobolev norm, but it's actually a Hilbert space with respect to the norm coming from just this term. Okay. All right, and that's important, for instance, if you want to show existence of weak solutions to elliptic boundary value problems. It comes in very handy. Another reason why one might be interested in this inequality is that the best constant in here is actually interesting. So one actually doesn't look at the best constant C, but one looks at the following. Lambda sub 1 of D is given, defined as the infimum over the gradient of F squared L2 norm over F, where F is in H10D without 0, obviously. And then, obviously, that's not the best constant for the Poincaré inequality. It's 1 over the square of the best constant. What's that? Oh, no. Yes, of course. Thank you. This constant is of interest in the following way. First of all, Poincaré inequality holds if and only if that constant now is positive. And this means that lambda 1 of D is attained at some psi in this Sobolev space. And psi with this lambda 1D solves a very particular boundary value problem in the weak sense. So psi lambda D solves the weak eigenvalue problem for the Dirichlet-Laplacian. So let me just write this. All this phi plus lambda phi is equal to 0 in D and phi equal to 0 on the boundary. Now, of course, saying that that makes that number and the Poincaré inequality interesting doesn't make it interesting just because it solves another problem. It is interesting because if you are in the situation where your weak solution is actually a strong solution, it can have physical meaning. So for instance, if D is just some nice set in R2, and you understand it as a membrane with fixed boundaries, or you have a drum, and you happen to know what this number here is, then you actually also know what the lowest eigenfrequency of that drum is, the lowest tone that drum can generate. But that only happens if the problem is not just weakly solvable, but actually strongly solvable. And in general, there's an immense amount of papers on estimates on lambda d under various geometric conditions on the domain. And the purpose of my talk is sort of close some, how do you call it, disknowledge, unknown things with respect to when does the Poincaré inequality hold for unbounded domains with, in particular, non-nice boundaries, so you don't assume anything on the regularity of the domain. And so to get to that point where we can formulate that in potential theoretic terms, so at the end of the lecture, hopefully, if I throw a domain or an open set at you and you have some understanding of potential theory, you can tell, does the Poincaré inequality hold or not? And to get to that point, let's start just with some simple and basic observations to get a feeling for when this inequality holds. Okay, so just some basic observations. Let's start with let's say we're just on an interval. That's usually the first thing you learn in some PDE course. So say F is smooth with compact support on that interval. Then we have the wonderful fundamental theorem of calculus, which tells us that we can write this as this integral. And we don't care about A because we have compactly supported. All right. But we want to estimate the L2 of this, so I first start with the absolute value. That is easy enough. I actually need to have the square in here. I would like to do lazy mathematics, so maybe I can just put the square in here, which of course I can't. But then we have Hölder inequality, so we can actually correctly do this. And now we are almost done. We just need to integrate on both sides now. Over the interval a to b. And before I do that, I notice I have this for all x. So in particular, I can substitute this by b. And now we just integrate from a to b, dx. And this is just a constant. And we integrate here from a to b. And we are done after I computed this beforehand, not just now. That is b minus a squared over 2. All right, and so we immediately have the Poincaré inequality holds for D. And if you think about it a little bit further, you immediately also get that it holds for any domain D in Rn, which is bounded in one direction. So 2, suppose D looks like A less than dot product x with some vector v. So here for some A and B in R and some vector v in Rn, probably not 0. Then in v direction we are bounded, and you can pretty much repeat this proof. If you don't see it right away, just assume you have the boundedness happening in the first component and just integrate over the rest of it. This formulation, as far as I can tell, is actually what appeared in Poincaré's work, or Poincaré in 1890, and then later in Friedrichs. And you can find it under Poincaré inequality. You can also find a lot of opinions about why it shouldn't be Poincaré inequality, but Friedrichs inequality. And then there's, I misspelled Friedrich, even though I'm German. I also saw that Steklov probably did it in his diploma thesis, which I then would think would also be 19th century. But yeah. Okay, so we have a couple of domains where we understand this inequality holds. Next basic observation is that a domain can be too thick for the inequality to hold. So for instance, not just for instance, what I mean by that is suppose you have a sequence xj in D and rj in R plus, such that rj goes to infinity, and that's the actual assumption here, these balls with some center xj, but large radius rj, are contained in D, then it actually follows that dagger cannot hold. And that one can also easily see, so you take some function which is non-trivial with support in the unit ball, and then you define some other functions on that using that sequence of points and radii. Then these new functions are compactly supported in these balls. And again, those balls become larger and larger and larger by assumption. And now if you compute the Altoonum of fj in terms of the Altoonum of f, it's just a, how do you call it, substitution. And when you compute that out, it is just this. And similarly, when you compute the gradient of this, you also get this from the substitution, but you get some extra r to the -1 from the derivative acting on this thing over here. And so if this was dominated by this, then this would need to be dominated by this, but that's impossible because this goes to infinity and this goes to infinity slower. Okay? So the moment you have large balls, arbitrarily large balls in your domain, the Poincaré inequality fails. Now, if you look back at this over here, so this says it's bounded in one direction, but you could imagine that the direction actually could change, right? It could be bounded over here in this direction, then it's bounded in a different direction. You could have some meandering domain, and it feels like you should still be able to do something like this. And in particular, you might start thinking about what's called the in radius of an open set. So you might look at the following things, so definition, in radius of an open set D is, I want to call it that here, R sub D is just the largest radius of a ball you can put in to your domain. So B XR is in D for some X in D. And you could conjecture that that might be enough to get the Poincaré inequality. Okay. What we do know, note, what we just showed is that if the Poincaré inequality holds, then the in radius is finite, right? You can't have arbitrarily large balls. So it's finite. However, the other implication does not hold, and that one can see if you look at the Rn without Cn and n larger or equal to 2. Then one actually knows that the Sobolev 1 space of Rn, well, let me not rewrite this, of D is actually the same as this space. if the spaces are the same, the Poincaré inequality must be the same. And we know the Poincaré inequality doesn't hold on Rn because it has infinite inner radius. So this example shows that Rd finite does not imply that the Poincaré inequality holds. So just as a preview, this must be somehow about what kind of set the Zn's are. And you might have noticed that I excluded n larger or equal to 2. If I'm in one dimension and I have the interval, open interval AB, BC, I cannot extend all functions in the Sobolev-1 space with coming from the complex support over that point. But in higher dimensions, I can always extend over a point. And good news is that sometimes the inner radius is enough. If your open set D is nice enough, then, and by nice enough here, I mean, so if D in Rn satisfies the exterior uniform cone condition, and the inner radius is finite, then the Poincaré inequality holds. And that means that on the complement of the domain or open set, you can always put uniformly same size cones on the outside of the boundary. So for instance, yes. So suppose your D looks like this, but there's a line removed. Then obviously you can't even put a cone anywhere. Or maybe you have some sort of cusp thing, and your domain, near that cusp looks like that. You can't put a cone there. And this goes back to, I don't think it's written down in the terms of using the word in radius, but it is contained implicitly in lecture notes by Agmon in 1965. Who is still alive, by the way? I somehow looked up who he is, and he is 101 years old, I believe.
Okay, so
yes.
The vertex of the cone
has to be on the boundary. Yes. So for each boundary point, you need to be able to find a cone where outside of the vertex, the cone lies in the complement, and you need the cones need to be uniform. So they can't, the length or whatever can't shrink to 0. Well, smoothly bounded domains would include they satisfy, oh no, not at infinity actually, not at infinity, yeah. Well, I get to those ones when I tell you the theorem. Okay, very good. And so for the theorem, we look at a version of the in radius which sort of manages to see the potential theory which is happening. In particular, it ignores polar sets. So definition is as follows. So I call this the capacitory in radius of D. And right, rows of D is the supremum over those R such that for all epsilon larger than 0, there exists an X in D such that the capacity of the ball at X with this radius R intersected with the complement is less than epsilon. I feel like I'm drying out in this room. Now that looks a little bit like a very cumbersome definition. Let me first say capacity. So maybe I should first say this definition stems from a paper I did with Dirichlet-Laplacian and Kaushik-Ramachandran in 21, where we thought about this question in dimension 2. Capacity is a notion which measures how nonpolar a set is. So in particular, if your set is polar, the capacity is 0. And the moment your set is, the capacity is non-zero, you have a nonpolar set. And my intention is to define this more exactly later, not at this point, and first actually say what the theorem is so that you're motivated to understand the definition of capacity. All right. So, as I said, this looks maybe harder than it is. So let's look at some remarks here. So note, there's many things to note. First of all, for the in radius, we needed to define the in radius in such a way that x is always in D, right? If I take the unit disk, of course the in radius is 1. If I take the punctured unit disk, then the in radius is 1/2. You can't take the ball with center, which doesn't belong to the open set you're looking at. Over here, you can actually ignore whether x belongs to D or not, because it doesn't matter if the center of that ball belongs to the set or to the complement or not, because a point is just polar and doesn't contribute to the capacity. Okay. The next thing you might note is let's look at what it means to have finite capacitory in radius. So say m is larger than that. You choose some m larger than that in radius. And formally, this says x is some epsilon larger than 0, such that for all x in D, this capacity of the set which lies in the complement is larger or equal to epsilon. This means I look at my open set D, I take any point in that set D, I look within m units, and I must find something in the complement, some compact set K, such that the capacity of that is larger or equal to epsilon. That means the complement is nicely distributed over the space, so to speak. Wherever I go, if I walk m units, I must meet something which is of capacity at least epsilon, a uniform epsilon. Okay. And so, let's see. Over here, we realized we couldn't use the in radius as a sufficient condition for the Poincaré inequality to hold by this counterexample. If I look at the capacitory in radius for this set, what is that? It's infinity because z to the n is a polar set. Right? I could also look at, say, d equal to Rn, and then let's say I subtract some balls, m is in Cn. Then I have a lot of little balls in the complement. They're nicely distributed. Their centers are always at the Zn points. However, the capacity of the complement is not uniformly bounded from below because I chose the radii to go to 0. If I would have just put some epsilon here, I would have had a finite capacitory in radius. But for this one, we still get infinite capacitory in radius, because when I go far out in Rn, I can go further and further, and at some point I have an infinitely large ball lying in my set. And then maybe one more example. A positive example, say we are just in R2, and I take out union. Okay, we're on R2. Math is hard. Minus epsilon and plus epsilon. So there's an interval, comma, n. Maybe I should put the cross product there to make this more clear. Yeah, let's do that. Maybe like this. So I take little line segments, which I distribute over the space. And the length of the line segment is all epsilon. A line segment in R2 has positive capacity, maybe epsilon over 4. And so here we have that the capacitory in radius actually is finite. Okay. Now comes the payoff. Now that we hopefully understood capacitory in radius, we can tell when a set satisfies Poincaré inequality. Okay, theorem. Part of the theorem is due to the work with Label and Ramachandran. It's 21, and part of it is due to myself. So, very simple hypothesis: D is an open set. D in Rn, n larger or equal to 2, be open. In n equal to 1, 1 is done, right? We know that on a finite interval, Poincaré inequality holds, and we know that on an infinite interval, Poincaré inequality can't hold because you have infinitely large balls in there. Right, so here, then, the following are equivalent. 1, of course, Poincaré inequality holds. So let me write this down one more time. Holds on D. 2, the capacitory in radius is finite. 3, is another potential theoretic condition in a slightly different flavor. There exists a phi, which is smooth in D, bounded, and the Laplace of phi is larger than C, which is positive on D. So in a bounded domain, it of course just means you have a bounded, strictly subharmonic function. For unbounded domains, it's a little bit more because you don't allow that the Laplace goes to 0 from the right-hand side as you walk out in the space. Okay, and then we have 2 more conditions. 4, which are the weak maximal extension of the exterior derivative on n-1 forms as closed range in L2 on the n forms. And then last one for all the complex analysts, if the dimension is actually even, then all of this is also equivalent to the weak maximal extension of d bar, the Cauchy-Riemann operator, on 0, m-1 forms has closed range in L2, and then it lands in M forms D. I feel like conditions 4 and 5 are just reformulations without enlightenment, so to speak, because just because I know d bar has closed range on some set, I don't know anything in the sense of I cannot tell from looking at the set if it's true or not. While with this one here, that feels like you sort of understand what's going on, in my opinion. So let's see. The work with Label and Ramachandran, as I said earlier, we did the case n equal to 2, but we didn't realize all the equivalences. So we did 1 through 3 and 5. Originally, we were interested just actually in the closed range property for d bar. In higher dimensions, you might want to understand when does d bar have closed range on functions on unbounded domains. That's still not known. And to understand that in higher dimensions, I thought, oh, we should just think about this problem in one dimension. It should be easier, and then we'll see what we take from that. And we realized very late in the game that actually you have an equivalence to the Poincaré inequality, and somehow missed that one actually could formulate it this way. Anyway, so we had those equivalences, and then at some point I realized that 4 is an equivalence in the case dimension 2, and having that at hand, I was able to prove everything else too. So in the higher dimensions. So in this context, I need to mention the work of Marja and Shubin. Vladimir Marja, I don't know what the first name is of Shubin, or was. So they proved something related in 2005, and not that it matters, but just a year before that, I actually took a graduate course with Vladimir Marja, who had a 5-year position at Ohio State. Right. So what these two did is they also looked at the notion of capacitory in radius. But on the one hand, they used a different notion of capacity, the so-called Wiener capacity, while we used in 2 dimensions what's called the logarithmic capacity, and in higher dimensions the Newtonian capacity. These are equivalent but different capacities, and the way they defined their in radius is, I would say, more difficult to understand, and their estimates in one direction are better, and in the other direction are worse. So let me formulate this a little bit better here. Right. So Marja and Shubin in 2005, they defined a different notion of capacitory in radius. Let me write it as rho sub d, comma gamma, tilde just because it's different. And their notion depended on the parameter gamma, which is some number between 0 and 1. And then they showed that if this is finite, it's equivalent to the Poincaré inequality to hold. And this holds for all gamma, and then they understand that their in radius, so to speak, is, if the in radius is finite for one gamma, it must be finite for another gamma. But it's relatively hard to understand from my point of view. And maybe I should still say, though, that they get some constant C1 is less than lambda 1d is less than some constant C2 so it's a paper full of estimates where they keep track of these constants, but so they have estimates for the constants. This here is, so to speak, the equivalence that if this is finite, you get a lower bound for this eigenvalue, right? And then if the eigenvalue, this is obviously a different argument, so let me write a corollary here, Gallagher, the following way. If D in Rn is open, then one gets that lambda 1 of D is less than lambda 1 of the unit ball times the capacitory in radius to the -2 defined by Jiří Lebel, Kaushik, Ramachandran, and myself. So this is different than having some nebulous constant hanging in here. And so in particular, it is different because, first of all, it's attained, right? If D itself is the ball, the unit ball, this is 1. And the next thing is that it's an if and only if in a certain way. So if equality holds, then D equals some ball at some point with this radius, capacitory in radius, minus some set K, where K is polar. And so for this estimate, the notion of capacitory in radius we used is better. For this estimate, I can't even get close to this power in the way I prove that the finiteness of this implies that this is bounded away from 0. All right, and now I have. What's that? One can easily see when one looks at the definitions that if R rho D is finite, then this is finite for some gamma. The other direction always holds, no matter what gamma I use over there, one can always show this direction, but this is restricted. But once you know this, the gamma falls out because the set of inequalities is independent of gamma. Yes. So you're asking if, yes, I do, but my powers are not as nice. And I didn't write it down explicitly because it is nasty, and I think I have enough time to get to the point where you can see that maybe this can be done better. Okay, all right. So I have 10 minutes, and let me just say, let me just hand wave this. If I have the Poincaré inequality, let me just write it here for a second. then it's not far-fetched to substitute this nabla here by the strong minimal extension of the exterior derivative of functions. So you might just write, instead of the gradient, you just write the modern language term for the gradient, and with compact support, so you're in the right space. And then this is the domain of this operator by definition. And the kernel of this operator is just a zero function. There's no other constant function belonging to this space. So this Poincaré inequality is equivalent to this having a closed range. And then via the Hodge-Star operator, you actually can go to the end of the D complex, and you get that D star acting on n forms has closed range, and then that, of course, means that this has closed range. And a similar argument works here because, let me just say, as Amy said this morning, on n forms, you pretty much have the Dirichlet problem, so you can prove this similarly, okay? Did you want to say something? No.
You're just using derivative.
Yeah. Oh, I probably could do something there, but I don't. Yeah. As a non-academic, I have a hard time with Mars Sinai. They don't let me in. So literature search is a big problem. Yeah, I don't know. Okay. So maybe, we can also hand wave this because we are all complex analytica. This pretty much you can show by a Hermander estimate, right? Just for the D complex for the D complex on n forms. So it's really just a L2 weighted estimate on D star on n forms, because obviously D on n forms is just 0. Right? So this is believable, and I want to point out that Sean Curry at some point pointed to me out a much quicker proof than Hermander's in this context by Lee in some very nice lecture notes on Fredholm operators. Right? Okay, and so we are left with, we know this implies the Poincaré inequality, and now the question is, for instance, if I know that the capacitory in radius is finite, how do I get these functions? One could ask. And this is where the bad estimates come in, so to speak. Good enough for the equivalence, but not good enough to say something as nice as Marjan-Shubin. Right. And do this. Right. And so there you need to know a little bit of what capacity is. And so I'm now only going to look at n larger or equal to 3 so that I can fix the notion of capacity I'm going to use. And so let me just quickly sketch this. So suppose you take some compact set in Rn. You should imagine that these are the nicely distributed sets in the complement. And let's say nu is a Borel probability measure with support in K. Then the potential associated to this measure is defined as the convolution with the fundamental solution of the Laplace operator against the given measure. And the total energy for this charge, if you will, is then given as I nu of this integral, d nu x, d nu x. And then one can finally define the capacity of that set K as the supremum of 1 over these measures. And then there is so-called Frostman's theorem, which tells you that if K is a non-polar set, you actually have a measure at which this supremum is attained. And so that is the so-called equilibrium measure. So equilibrium measure for K, so the capacity of K is then given as 1 over I of mu, and this is for K non-polar. And I feel like you could just accept these words and just look at the functions given by P for a given equilibrium measure. That's where the magic lies. These functions P are harmonic away from the compact set K. Moreover, if you use the equilibrium measure, you actually have that these functions, so now it's P sub mu because you're using the equilibrium measure, these functions are bounded. And now you're almost already in the set of having something nicely subharmonic and bounded with which you can do Hermander estimates. So P mu is harmonic on K, not on K, on the complement of K. And at the same time, they're non-negative functions and they're actually bounded above, that's a theorem, by the capacity of that set you're looking at. So they're nicely bounded as long as your capacity doesn't go to 0, as long as K doesn't become polar. And they're harmonic, so you could just look at nice compositions of these functions and look at the Laplace of this. Then, obviously, this is just chi prime of P mu. And then you have something almost wonderful here. This, unless the gradient vanishes, which it shouldn't do too much, is something positive. And with a little bit of work, if you take some set K, say this is your set K, and you take a large enough ball around it, one can show that this here is actually positive as long as you stay outside that ball. Okay? And we are in a situation where we have these compact sets K nicely distributed over our whole space. So, when RD is finite, I can put a lattice on my space, but the length is larger than the capacitory in radius. Then I know that in each of these things I have some non-polar compact set. I can count them up because I have a lattice, right? So I have some kj's. I have the associated potential of the equilibrium measures. And I can then look at the sum of chi composed with P mu j. And now I just need to choose chi in such a way that I actually can sum up an infinite thing here, such that I get something bounded, because I need something bounded, and such that I get something strictly subharmonic. And that's it. And who was it? Gian Maria has left the room. Oh, there you are. So in the end, I use something e to the minus 1 over delta P mu sub j as the chi in here, so to speak. And that's, as an infinite sum, is just incredibly hard to estimate what you actually have there as your upper and lower bounds. You can estimate it, but maybe I'm too old, I don't have the patience anymore. I haven't sat through it to see if I can rediscover what Marsha and Shubin do. And it's 2:50. Thank you very much for your attention.